Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we are going to take a look at Minitab again today, and I've had a request specifically to do a DOE analysis, to do some factorial plots, and to do an interaction plot as well. So we're going to do some analysis on some data that someone's sent to me, and I'm going to just demonstrate where to get these plots from. So that's the story of today's newsletter. Before we start, because we're covering DOE today, my new book, Design of Experiments for 21st Century Engineers, great practical text, really simple, keep the mathematics light, keep the money-making procedures to the max. Design of Experiments for 21st Century Engineers, just published. You can get it from lulu.com. So please go and buy that text straight after this video. So let's have a look. We're going to do DOE. We're going to use Minitab. Let's be clear, it's a 2 to the 3 full factorial. I'm going to create a regression model. I'm going to create a factorial plot. Interaction plot. And a surface plot. Okay, so simple software tutorial covering off those DOE points. Let's get into this example right now. Okay, here's the data set that we're going to analyze. As I mentioned earlier, it's a 2 to the 3 full factorial. You can see currently I've got this set in Excel, and the reason for that is because I like to see it as a table, and this would be the normal way I would analyze it. I would normally use some Excel based software, but I'm going to show you Minitab today. But I just want to show you just practical. Let's keep this practical. A lot of DOE and things like that, it's very statistical. The mathematicians and the statisticians want to teach you all the numbers and the R-squared values and things like that. But one of the things I like to do is to keep this very, very practical. And having the data in a table like this is part of it being very practical, and so you can think sensibly about what's going on. So the actual DOE itself, of course, is in this array here on the left hand side. My data is in the yellow fields, and you can see 4 columns of data, which means that what I did was I collected 4 data points for each setup. So if I look across the row here, setup number 1, I collected 8, 9.2, 14.2 and 10.6 as the 4 results. And as I say, this is a good way to look at the data. Minitab is going to put this data in a different orientation, but I want to see it as a table before I let Minitab have the data. So let me just show you what I'm doing with this data before we start, and then I'll tell you what Minitab is going to do when we set that up. So the reason why I want to do this is because I want to look across the row of the 4 data points, and I want to look at them all together. Now if you look at the 4 on the first row, I do have a concern. You've got 8, you got 9.2, you got 10.6, but then you got 14.2 there. Now that's a strange data point. I'm not particularly happy with that. But by the way, this isn't the worst data that's on this page, because look, the next one down, 26, 33, 28 on the far side, but then mixed in with them is 40. which is well away from the other results. Now this is a sign maybe things were going wrong in the DOE. Maybe I've got measurement system problems. So this is a little bit of a red flag to me when I get spurious data points. By the way, this could be something simple like a typographical error. So you might have typed in 40 when you meant to type in 34. And so that's the other reason why you want to see these data points. You're just simply checking for simple errors like have I typed all the right numbers in as well. So I like to look across the row to see if there's any nonsense in there. The other thing I like to do is I want to check that the process got moved around. Remember, the variables that you chose over here should have been variables that with your engineering knowledge, with your knowledge of the physics, these variables do something to the process. They move the process around. Now, one of the key points about the DOE is that these values should be a little bit extreme. So you can see on the infill, look, the person who's given me this data set, they've gone from 5 to 100. That's a nice extreme setting. Now think about it. If you're moving these important variables to extreme places, then what you should see across the data table is lots of different results. So for instance, look on row 1, we're as low as 10, but the next row down, we're up at 32. Then we go to 15, then we go to 44, 13.9, 25, 16, 42. Now that's a nice data set. What it's telling me is the process got moved around by the 3 variables on the left hand side. And that's also a good thing to see. So we want to do, before we start doing any statistical analysis, and you could do some statistical analysis to get the same information that I've just done by eye, but use your common sense first. Get attached to the data set. Don't just let the maths run away with the analysis without you thinking clearly about what you're doing. Now let's talk about what Minitab is going to do with this data, because it isn't going to put it in a table like that. So let me draw you a diagram of what Minitab is going to do for you. So what Minitab's going to do, you're going to have this is what I've got currently. I've got the array. And of course I've got these 4 columns, which are the replicates. 4 replicates across the row. Now, by the way, if you happen to use the Taguchi DOEs, of course, in Minitab, this is exactly the way Minitab will present the data to you. But if you happen to choose classical, so if you go to the factorial menu, which is we're going to use today, what it's going to do is this, look. When you tell it how many replicates you have, it will repeat the array 4 times down the spreadsheet, down the worksheet, and then against the second repetition of the array comes data set 2. Then it'll put replicate 3 in there, and finally, of course, it'll put replicate 4 in there. So what you end up with is all the data in one column. So you can't do what I just said, which is look across the row and look for signals for each setup, because the arrays are all mixed up on the column. And this would be even more true if you decided to randomize all of this, which is the other choice in Minitab. I'm not going to randomize today, but that's how Minitab is going to set the data up, and then we're going to analyze the data from there. So let's put this information into Minitab, and then let's generate a model, and let's do the interaction graphs, let's do the surface plot, and we can show you where to find those and how to do them. Okay, So here we are in Minitab now, and the first thing we want to do is to set the DOE pattern up. It's full factorial, so we're going to go Stat, DOE, Factorial, Create Factorial Design. And you can see there, like I said, 2-level factorial, and number of factors, well, we've got 3 factors. It then says designs, so let me take a look at the one. I've got a half fraction or a full factorial. The half fraction, resolution 3, it is a DOE I would never ever use. It is not necessary to do things like that today. Way too risky, lots of aliasing that you really don't want. So I'm going to pick the full factorial. I'm just doing a straight 2-level DOE, so no center points are needed. Number of replicates, well, of course, it was 4. I'm going to leave the blocks at 1. I'm going to click OK. Now the other menu items appear. So let's take you through them. I'm going to look at the options first. And the key point about the options, I'm going to switch off the randomization, just to make it a little bit more easier to see what's going on. Then what I'm going to do, I've got to tell it the factor names, and I've got to tell it the levels. So the first one that we're going to do, I'm going to put the nozzle in. It's numeric. So this is nozzle diameter, 0.2 to 1 millimeter. Then we're going to do orientation. Again, it's numeric, 0 degrees to 90 degrees. Then we're going to do infill. And infill is 5 to 100. Now, just before I click off this, the more eagle-eyed amongst you will notice that I've put these 3 variables in the opposite order to what they were in my Excel spreadsheet. And that's because the pattern as it comes up in my software is the other way around. The columns are in the reverse order. So I've put these in reverse order so that all the data will make sense when we paste it into the worksheet. So click OK to that now. So I'll put the factors in. Let's take a look at the results. It's just giving me some options there as to some things I might want. I don't change any of those things. I don't use this particular menu at all. So click OK, and then we can click OK, and it will give us the pattern. So let's show you. It's telling you, look, all terms are free from aliasing. Well, you would expect that because this is a full factorial. So now you can see, here's the pattern. And it's been multiplied. You can see, look, 32 rows. It's been multiplied 4 times down the table. So now what I have to do is to paste the results into, I'm going to paste them into C9. I'm just going to call them Y1 in this case. So I'm just going to take them out of Excel, and one at a time I can just paste the columns below one another like that. So you'll see me finish that off now, and then we'll do the analysis. So that data's typed in now. So it's in this column format as I mentioned to you earlier. And now what we're going to do is now we're going to do some analysis. So let's go to DOE and let's do some analysis on this. So factorial, and now you can see that some of the other menu items are alive. You can see that the way Minitab works, things like factorial plots, I can't do a factorial plot effectively until I've done a model. So I'm going to have to do some mathematical analysis on this. So I'm going to have to go analyze factorial design. I obviously need to tell it that the response is in Y1. And then we can go take a look at what we're doing here. So here are the terms that I can analyze. So because it's a full factorial, I've got the main effects, all the 2 ways and the 3 way. I'm going to leave that as it is because I want to do full analysis. Let's go across this. There's some certain things here that I don't use. The covariates I don't use. Let's have a look at the options. Transforming the data. Don't want to do that. That's fine. The graphs. Well, the Pareto of the effects is a useful little chart. That's the only thing I'm going to ask it to really do. I'm not going to change anything there. On the results. Now on the results, I'm going to turn most of this off. So I turn everything off except the coefficients. Now what that's going to do basically is just show me a regression equation. Now you'll notice I didn't switch the regression equation on. It does a very strange thing in Minitab. It builds a bit of a weird regression equation that's not very easy to read. Whereas the coefficients table, it's very easy to read. You can see the model from the coefficients table. So that's the only thing I ask for in the results feature. Don't do ANOVA. Again, there's certain things you could do. This is kind of an analysis which is for the people with much more deeper understanding, analysing the residuals, looking for leverage. Now leverage, by the way, is based on that thing I was looking at earlier. So practically I was looking at outlying data points, but you can do a mathematical calculation for leverage. You can also do something called Cook's distance, Cook's D, that also looks at leverage. And so those two analyses could do a mathematical version of using your common sense. But initially, I like to use my common sense. I'm not going to switch any of those on because it's kind of a little advanced thing, so I'm going to leave that. And now we're just going to click OK. And if I just get the data out of the way. Okay, now here is, now the coefficient column, that's the model. So that's the regression model. So this particular data set, and by the way, I haven't told you what the process is. This is a client's data set. So I'm not being too specific about what the process is and what we're trying to achieve. But the target in the coefficient, look, the target can be hit by the equation that says 24.9 plus 10.9 nozzle plus 4.5 orientation minus 0.6 infill, etc. So you can just read the equation off the column there. Now obviously we've got p-values that allows us to model build, and really infill should be taken out of the model. Infill orientation two-way should go out of the model. So those two terms should go out of the model. So should nozzle and orientation. So using the p-values, I would normally reduce the model down to remove terms that really shouldn't be there. And let's take a look at the Pareto below. So the Pareto, look, is showing us the important terms. So the things that I just said to take out, the three-way, the infill and the BC interaction, they should be removed because they're below that red line. You see that 2.06, that value there. That value is there helping you to decide what terms should be removed from the model, what terms should stay in the model. So terms that should stay in the model are the A, the B, the AB interaction and the AC. So that Pareto is quite a nice little tool to use. Again, use common sense. You can easily see that A, the nozzle diameter, is having the biggest effect on this particular process. And if you look at the standardized effect down here on the scale, it's moving the process by 20 odd units, whatever you were moving the process in, by the way. So if you look at the coefficient, look, 10.9, that is whatever units you were measuring. So if you were measuring millimeters here, you were trying to hit a millimeter target, then this particular variable, nozzle diameter, is moving the results not just by 10.9 millimeters, but by twice 10.9 millimeters. That's why the Pareto is up at 20 odd, because two 10.9s add up to 21 point something, 21.8. You can see, look, it's in the effect here actually. There's the value there, look. So there's the model, and you can reduce the model down. But the reason I wanted to do this little example was to show you the plots. So let me go Stat, DOE Factorial. Now you can see, look, the factorial plots are available now that we've created a model. So let me go click on that menu item there, and it says, well, okay, what factorial plots would you like? So normally you'd want all three of the main effects, and at the moment, look, it says terms to display only the model terms, and you could ask for all terms. Well, at the moment that is the same thing, because I haven't taken any terms out of the model. I haven't removed anything out of the model yet. So of course, if I ask for this, it's going to give me all the main effects, and it's going to give me all the two-way interaction graphs as well, I think. But I have to go and ask for them. I'm just going to have a look at the graphs, and it says, what would you like? Main effects plot, interaction plot. So I could switch the interaction plots off if I didn't want to see this. If it was a slightly bigger DOE where there's lots and lots of interaction plots, I might switch this off and then just ask for one or two interaction plots specifically later. But I'm going to ask for everything because it's just a 2 to the 3 full factorial, and there's not too many diagrams in this case. So I click OK, click OK again, and now look, what do I get? Well, I get, so I'll pop that out, main effects plot. There it is. So again, look, it's telling me the longest line on this diagram is the most important variable. You can see the nozzle diameter, which we've already talked about, is moving the result over 20 units. And you can see, look, if we look at the data point down at the bottom, which is, if I point at it, give me a value, there you go, 14.01, all the way up to 35.8. It's out, you know, it's over 20 points that it's getting moved around. The longer the line, the more influential the variable is. So that's the main effects plot. Below that, I'm going to get the interaction plots. So you can see the three interaction plots. The nozzle and the orientation probably is the one that I'm more interested in. This is the BC interaction, which is also a term that would remain in the model. So the BC interaction is definitely happening. You can see the interaction plot there, which is super useful. Again, if you click on this, it'll pop it out. Can you make it full screen? I think you can. Yeah, so it's a lot easier to take a look at there. Now, I'm also going to look at the three-dimensional version of that two-way interaction, nozzle orientation. So I'm going to get it to draw me the surface plot. So if I go back, DOE Factorial. Now the surface plot is a separate request here, look. So surface plot. Okay, so nozzle orientation. Now that's the way the interaction plot is drawn up in that top left hand corner, nozzle orientation. So I'm going to leave it as nozzle. I could put it the other way around, by the way. I could put it orientation nozzle, and it'll give me a different looking picture. You know, it's the diagram's not shown here, but it's a different way of looking at the data set, even though the interaction is the same. So just a tip for you, go and have a look at these diagrams, play around, put orientation in the first one and nozzle in the second one, see how it changes the picture of the data that you're getting. So let's just have a look what the menu items do for us. The first one, now this is quite a useful one, because obviously you're plotting two variables out of the three, and the infill has got to be somewhere. Now in this case, the infill is being left at the midpoint, but you could put the infill to 100, you could put the infill down to 5, you can put the infill at any level you wish to do. Now we'll talk about that in a second, but I think the first thing you'd want to do is just leave the infill where it is at the midpoint, and then we'll take a look at the diagram and we'll talk about how you can change the infill and what it will do to the diagram that we've created. Options, well, that's just a title. I'm not going to give it a title in this case, and I'm not going to look at I don't need to look at the model, so I'm just going to click OK. So there we go. Now what this is a three-dimensional diagram of that interaction plot. So okay, I've taken the diagram out and I've put it into PowerPoint, and that just allows me to make a sketch. So if you looked at the interaction plot, the interaction plot sort of looks something like this, didn't it? Okay, so that diagram, this one over here on the left, that's a three-dimensional version of that interaction plot. So one of those lines, so number 1, will be the slightly flatter slope. It's this edge here. The second line, line 2, is the back edge. This is the one that's slightly more upright. But now what you can see is the complete plane of all the results you could get for moving orientation and nozzle diameter. Now this technique was invented by George Box back in the 1950s, and one of the reasons he did this was to assume that this diagram is actually part of a hill. So if you imagine a hill, maybe doing this, and what you're trying to do is to get to the top of the hill. Maybe your ultimate achievement is to try and find the maximum point in your system, and at this point you've done an initial test in an initial design space. So you've gone from here to here, so you've gone from on the nozzle diameter 0.2 to 1 millimeter, and you've gone on the orientation, you've gone 0 to 90 degrees, and that was your initial thoughts on where you'd like to gather information. But of course you didn't know what you were going to see when you gathered this information. Well, now what this is telling you, look at this picture. It's saying if you want to go higher, that's the direction you need to travel in. In other words, you need to get the orientation above 90 degrees, and you need to get the nozzle diameter above 1 millimeter. Now this is the easiest way to see this piece of information. You can use models. The model, if you look at it and you kind of understand it a little bit, you can use the model to try and understand this. But this is the best way to see where the next DOE might take place. So what you might do now is do a designed experiment over in this region, and see if you capture that. See if you capture that maximum. See if you capture that maximum point. So it's the idea of being able to visualize your route up the mountain, or indeed down the mountain if you're looking for the minimum. Value. So that's what these surface plots are for, and today they are still really useful for this type of thing. In the days when they were trying to optimize, they were trying to find an optimum point, they would also find these techniques very useful when they were trying to do manual calculations. Today we don't need to use them for this technique, because today the software will find an optimized point for you. So we use software today where we'd use diagrams back in the 50s and the 60s. But the idea of where's the next DOE got to be, where is my next area of interest, is one of the great uses for the surface plot. Now I mentioned earlier that we'd fixed the infill to 52.5, and I said, well, we might change that later. Now you'll notice, look, this is almost like sitting in this is like a lift shaft almost. Think of it like a lift shaft. If I changed that 52.5, what would I have done? Well, there's a good chance that this plane would move up the lift shaft. Or if I wound the infill in the right direction, this lift shaft, this plane would move down the lift shaft. So there might be a higher value, but 50 odd maybe, I don't know where it might go, if you move the infill. But that's why I said the first thing you want to do is just leave the infill at the midpoint, and maybe you can come back and adjust it later if you want to move this plane up and down in the column where it's sitting. But take your time with these things. If you move too many things too much, you sort of lose the plot of what's happening. I usually start very simple. I take the midpoint, I have a look at what the interaction is telling me, I have a look at maybe whether it's telling me there's a new region to test, etc. There might also be robust settings. Robust settings is when these diagrams go flat. So when the line goes flat here like this, this would be known as a robust setting. So these diagrams can be really useful. But there's the surface plot. If we go back to Minitab, there's the interaction plot, and of course above the interaction plot was the factorial plots, which is a pictorial representation of what you're seeing in the model effectively. So there's the latest Minitab tutorial. Obviously I'd be creating a better model, I'd be taking terms out of the model, etc. But I like to just show you these techniques a piece at a time, because often if you learn the full process of creating the DOE, doing the DOE, reducing the model, creating the diagrams, using the diagrams, finding robust settings, etc., 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 it could be a 1 hour 20 video. You're probably not going to watch it, and even if you do watch it, you're probably not going to remember it. So I like to do pieces. That's the main effects plot, the factorial interaction plots, and the surface plot using Minitab. Okay, well, I hope you enjoyed that little Minitab tutorial. If you've got any comments, any questions, please leave the comments below. Remember, design of experiments for 21st century engineers keeps it really simple and practical, and gets you into one of the best money-making tools you can ever use in any engineering situation. So there's your software of choice there, Minitab. There's the book that helps you with other parts of the subject as well. I would love for you to get into DOE because it really is a money-making monster.